Okay, then let's determine the other one, which is this alpha D. This is the coupling from the drain to the floating gate. And then we need to apply this equation. So from this equation, let's solve the alpha D. So you can get it. Alpha D equals to this delta VD, and then you have the delta VFG minus alpha CG delta VCG. Okay, so this is the equation for the alpha D, and then we are going to plug in the numbers here. So let's look at the denominator, the delta VD here. So we need to look at the 4 curves now, because here we are going to change the VD from 0.1 volt to 2 volts. The drain voltage, delta VD, is this 1.9. Because you change it from 0.1 to 2, so the delta VD is 1.9. And then if you change this delta VD by 1.9, so here the alpha CG is already calculated in the previous slide, which is this 0.83. Okay. So what we need is just the delta VFG and delta VCG. So delta VFG is the change of the floating gate voltage between, let's say, those two drain voltage from 0.1 volt to 2 volts. So with that, actually that means we need to look at the flash cell, and here those two are flash cell, and we have those, let's say, delta VFG. So this delta VFG actually is the delta VG, because we need to use the dummy cell to do this. So if you look at the dummy cell, which is this one, and we need to compare the solid line and the dashed line, okay, between those two drain voltage. So here, if we focus on this level, this current level, then this voltage shift from here to here. Those two blue dashed line is the voltage shift, which is from here 1.7 and 1.1. So this is how you get here. And similarly for this delta VCG, this is from the flash cell. And the flash cell changed from this point to this point, those two red dashed line, and which is like 3.1 and 2.1. And then you can plug in the numbers here, and then you do the calculation. It's about 0.12, the coupling ratio. So I think you have to review this after class. And you have a homework on this floating gate versus the conventional MOSFET. So we will post that. And here the conclusion here is the drain coupling ratio is smaller. Of course, this is what you want, because you want the drain voltage to be less effective than the gate voltage, the control gate voltage, to tune the floating gate potential.
Sorry, why you choose this specific I? Is just an example, or?
Because I think this is near the threshold. Here this is this 10 to the power 5, negative 5 is close to the threshold, so you use that current.
Okay.
You want to, because here we are talking about the threshold voltage window, right? So you use the voltage close to the threshold. Okay. So next, we are going to discuss how we write the data into the flash. So we need to inject or eject electrons from the floating gate. And here are different mechanisms for the program and erase. Again, program is to inject electrons into floating gate. Erase is to remove or eject the electrons from the floating gate. So first one, for the injection electron to the floating gate, the first mechanism is this channel halting electron, CHE. And if you want to do this, you need to bias the floating gate with this kind of voltage. Of course, this is one example, but a typical voltage like this. Control gate like 12 volts, drain like 5 volts. So this transistor is on, and this transistor probably is in the saturation, and so you have large current. So electrons are flowing from the source to the drain. And since the drain voltage 5 volts is kind of large, so the electrons will be accelerated and get enough kinetic energy. So when the electron is approaching the drain, especially here, so then the electrons will become faster and faster. That means higher and higher kinetic energy. So if the electron has enough energy, it may jump over the barrier of this between the floating gate and the channel, that is the oxide barrier. So electrons may have enough kinetic energy to jump over this barrier and then inject to the floating gate. So this is the channel halting electron, and it's used in the NOR flash. And for the let's say ejection of the electron out from the floating gate, one mechanism is the source FN tunneling. So in this case, we'll apply, for example, 15 volts to the source and then ground the control gate. So electrons tend to go to higher potential, and then due to the tunneling, then electrons will be ejected out to the source. And this is also used in the NOR flash. And then for the NAND flash, the program mechanism is through this channel FN tunneling. So this one is simple. You just apply large enough voltage to your control gate. For example, in this case, 20 volts. So then the electrons will tunnel through this oxide to the floating gate. This is simply because the gate voltage is too large. So you have the probability for the electrons to tunnel through.
Is it because the band?
Yeah, we will talk about that in a minute. So the other way to erase is just to reverse the voltage polarity. For example, if you apply control gate negative 20 volts, or in some case, you can apply here with substrate positive 20 volts. Is the same thing as you apply negative voltage to the control gate. They are equivalent. So in this case, the electrons will be extracted from the floating gate to the substrate. So this is in the NAND flash. And this erase, because you apply positive 20 volts to your substrate, then that's a problem for the NAND flash. Because the substrate is shared. So when you apply 20 volts to the substrate, the whole block, let's say whole array, will be erased at the same time. So that's why the NAND flash is not random access. When you write 0 to 1, the whole array, all the data will become 1. So this is the NAND flash, write mechanism.
When you say you can just apply voltage on the gate.
But typically we don't have negative voltage on chip. So the FN tunneling, okay, this is a little bit device physics. So this Fowler Nordheim tunneling or FN tunneling is a mechanism for the electrons to tunnel through the barrier with a triangle shape. So this is between the substrate and the, let's say, I think this is the floating gate, and this is the substrate, and this is for the erase. So you apply 20 volts, for example, to your substrate. So this is, let's say you have, if you don't apply voltage, and roughly then the band will be lined up. Of course, a little bit of bending because the doping is different. One is, this is P-type, this is N-type. But roughly, the band is like this. This is from the floating gate to the terminal oxide, and this is a channel. So you know, oxide is a barrier to separate the floating gate and the channel. But when you apply really large voltage, positive voltage means pushing down the band. So then the barrier here will become triangle. The electrons will go through this triangle barrier because the tunneling probability is proportional to this distance. Of course, the barrier height as well, but this distance will matter. When you bend down the band, this will become triangle, one more triangle. Then this distance will become shorter. So the electrons will have exponentially increased probability to tunnel through due to the quantum mechanics. And this is called the FN tunneling, and if you derive the equation for the tunneling currents, so this is the equation, and there are some fitting parameters here, not fitting parameters, some constant related to the like effective mass and barrier height and so on. So, but the key is that this current is very exponentially depends on the field across the terminal oxide. So I will not go into the details of this equation, but I want to ask one question. Okay, so in this physical picture, okay, electrons can tunnel through like this. So in the valence band we have holes, right? For example, in the p-type substrate we have a lot of holes, right? The holes, can the holes tunnel through from the substrate to the floating gate in this case? Any idea? Why we talk about the flash, we talk about the electrons stored in the floating gate. We don't talk about the holes stored in the floating gate. Why is that?
Just the mass is so high, the tunnel probability is very low.
Of course, electron hole mass will be a little bit different. Typically, electrons mass a little bit smaller. So I think the reason is the barrier height. This guy here, this barrier for electron is 3.1 eV, and for hole is 3.8 eV. So you know the tunneling probability is proportional to those barrier heights. So the holes are more difficult to tunnel through in the conventional floating gate transistor if you use silicon. Okay. silicon and silicon dioxide as the tunneling oxide. So that's why in the conventional floating gate, we talk about the electrons stored in the floating gate. We don't talk about the holes, because holes are much more difficult to tunnel through.
Just want to make sure you said tunneling probability is proportional to, should be the height of that barrier, right? It's not
Height
the
and distance.
Because
Both.
the distance here didn't mean any physical meaning.
What do you mean? Distance is a physical meaning.
I mean, lateral.
On this one, kind
So this distance is very important, right, to determine the tunneling rate. If you go back to quantum mechanics. So what do you mean?
What was the scales mean? X directions, physical mean?
Thickness of your tunnel oxide, of your nanometer. The thickness of your oxide.
Okay.
So we draw it this way, but actually when you look at that structure, is this distance, right? This is the thickness of the tunnel oxide. So this is specific to this floating gate made by the silicon, but later we will talk about the charge trap cell. The industry already switched to different kinds of oxide, tunnel oxide, and then holes will tunnel through. In today's like charge trap or 3D NAND flash, holes are tunnel through these days. But for the conventional, traditional floating gate, only electrons, because of the material system here. Okay, so the FN tunneling, more details. I will skip the most of them. So, but if you want to draw the current, let's say, versus the electric field, because of this equation, you can, let's say, use this current divided by the electric field squared, and then you take the log. So versus 1 over E should be a straight line if it's F internally. And roughly experimentally, this is like what we showed here. Oh, sorry, this is the original IV, just the current and the field. But if you reorganize the y-axis to be the J divided by E squared, and then take the log scale, and then the x-axis become 1 over E, then this will become a straight line. So this is F internally, and it applies to this triangle barrier. But if this barrier is very thin, so electrons will see a trapezoidal shape of barrier. In this case, it's called direct tunneling. This happens when the oxide is very thin, like 2 or 3 nanometer. But in the flash, the oxide is thick, like 8 nanometer, 9 nanometer. So the direct tunneling will not happen. So only the FN tunneling will happen. So the reason, let me ask, why do you make the oxide like this thick?
So you can control tunneling. You only want the tunneling to happen when you apply a certain voltage.
So because we care about the retention of the data, you store the charge there. If the thickness is too thin, then the charge will automatically directly tunnel through. Then you will lose your data very easily. So you need a thick tunneling oxide to maintain the data retention. And only when you apply large enough voltage, then you make this barrier become triangle shape, and then you have large tunneling current. Then you program your device. Okay, so I think time is up, so we can stop here. And next Tuesday is your midterm exam.